Hey, everybody. I was going to say I will keep it short and brief because I know you guys want to get to the beer and pizza, but you already did. My name's Colin. I work for AppDynamics. I've been in performance engineering for quite a while. I'll talk to you a little bit about performance engineering, the SDLC. Just a few questions. How many of you consider yourselves on the ops side of DevOps? A few? Develop? Rest of you? Okay, a few. Some are agnostic, I see. How many of you are doing CI well, or you consider yourself to be doing CI very well? One hand, maybe a couple. Three. Yeah. Okay. And then from the CI, who is doing continuous deployment into pre-production with containers? All right, a few. How about production? One. Wow. Oof. All right. So, the challenge has been around for a while, and the containerization has really come a long way to meeting those challenges with regard to getting things into the DevOps lifecycle very quickly. And it's really transformative. However, is it ready for production? I would say within hosting organizations like Google, who pioneered this, it works really, really well. But in corporations, there's some challenges. What happened? Where do we go? There we are. Containers do require new development methodology, and they require that apps really be designed for horizontal scalability. There's still tooling challenges in corporate organizations. Why is this doing this? Still have to support Type 1 and Type 2 infrastructures. And because it's primarily open source, there's not a whole lot of support infrastructure yet. And so it works really, really well for organizations that are focusing on optimization and efficiency over really, choice of OS. So let's talk about the performance engineering aspect of things and what it takes to get these new models into production. Performance engineering is kind of like part mad scientist and I think, part politician. We really have to work across a lot of different organizations and groups within the environment to get things into production. And, coming from the ops side myself and having spent a lot of time in development as well, ops directors and managers don't like to put new systems into production that aren't really well vetted. And when you start getting into CI and CD and you really start focusing on automation, things that we have conquered and dealt with and challenged in the past really come up to play. And that is around capability of process, and all that is really focused around predictability. If you're going to do a lot of automation, your systems have to be predictable. And not that you need to go back and start implementing Six Sigma into your agile DevOps lifecycle, but you have to do a lot of measurements and a lot of inspections along the way. And you do need to really look at the statistics and the numbers and see, where things land. Software development lifecycle. One of my favorite quotes with respect to the performance engineering space is from Lord Kelvin, and it really speaks to the fact that you have to be able to speak intelligently. If you're going to get this stuff into production and you're going to get it into production successfully, you need to understand the basis of how it's going to perform, and you need to have some intelligence about what you're going after. So whenever we talk about performance engineering, it always comes down to metrics. And really good metrics have some really common traits. All metrics should really have underpinning goals that define them. Instead of just monitoring and looking at metrics, you really want to focus on what is the goal, what are you trying to achieve? And you need to continuously track it. Metrics need to be objective, measurable, meaningful, actionable. They should be simple. They shouldn't be complex metrics. and they should be able to calculate the value of automation. What I mean by that is that, the level of automation that you undertake into the production and pre-production lifecycle, there's a point where the cost of continuing to do automation is going to, you're not going to get 100% automation. I like to say automate nearly everything, but not everything, because trying to automate everything is too much. You probably won't get there, at least successfully and in the time that you need to. And so the things that you measure, should lend to that. There are important lifecycle metrics, application, software, automation, software testing metrics. This is not a course in that. But early life cycles really should focus on these as gating metrics, defect ratios and percent of test coverage and things of that nature. But as you get into application intelligence and APM platforms, these tools are going to measure thousands of metrics. Context is relevant, however. And when you are talking about automation, the right amount of simplicity is really important, I think. Response time, throughput, resource utilization, wait states, these are really important things. And if you can measure these discretely and you can measure them quickly, it's going to benefit you. All the other metrics are going to come in and really support those when they go wrong. So performance engineering lifecycle considerations. Define robust gating at every phase, and that's unit tests, integration tests, quality tests, functional tests, performance tests. And I really break performance tests out, and we'll talk about that. Metric variation needs to be known. It needs to have a common cause. In other words, if you have a lot of divergence in your metrics, if your metrics are all over the place, they don't make a whole lot of sense, and it's really hard to figure out what's going on. And it's probably because there's more than one thing that's changed in your environment. So you got to really have a tight grasp on change. Performance tests don't have to be full-size, complex, end-to-end tests all the time. A lot of organizations that I go into and consult with, that's kind of how they do things. They have a full-size production environment, they have a full-size pre-production environment, and they're testing at that load and capacity every time. It's hard to be lean and agile and do that. Kubernetes really, I think, helps to that, and containerization in general is really changing the landscape and what you can do in the pre-prod environment. The idea, though, is to get that to production as well. Every test should be designed to prove that something is not ready to go production. And there's a subtle mental shift here in that a lot of organizations and a lot of test engineering, quality engineering groups write tests to pass. They write performance tests to pass. Okay, well, we expect this much load. We anticipate this much. We're gonna see if we can get to that point rather than going past that point every time. So some best practices, define standards and adopt. All service endpoints should have, if not 70, some percentage of code coverage that is meaningful, that's measured, that's gated. Automated testing should include a lot of non-functional testing, performance testing, security testing. Green states really have to produce a high degree of confidence. I bet yours does. Yes. Yeah? Trying to? Okay. Yeah. And because green states should really bode well in terms of high confidence, organizationally, it should require, an act of God to get something that's not green into production. It should be a really big barrier to get around. Additional best practices, health checks, write intelligence in the application, have the endpoint be able to do a health check monitor that knows what its dependencies are and whether those dependencies are healthy. When it comes to performance engineering and performance management, the hardest thing to do is monitor something that's not deterministic, because then you're really left with just rate, and rate is subjective based on what's consuming that endpoint. Lazy interfaces like get all, don't do that. Get your developers not to do that. Bound your result sets, use pagination, do whatever you can do to try to make the response deterministic, even if it's asynchronous, because when you do that, It makes it really easy to measure response time, throughput, transaction per second rates, and really get a solid fix on what the environment is doing in peak and non-peak and downstream dependencies likewise. Have an up-to-date response plan for when things go wrong, and make sure that third-party integrations are bound by those same agreements that you have in terms of established SLAs. Yeah, I don't want to go to sleep. Not yet. And define response time targets as a standard practice within the organization, whether it's 800 milliseconds, whatever, because it's deterministic. You're setting those limits. You're saying, okay, what does it take to achieve that? In terms of performance testing, this is one of the slides that I show with a lot of people, and it makes a lot of sense, and there's a lot of information on this slide, and there's a lot of history behind this in developing this. Do discrete scale testing. Stress to your application, your endpoints. Use mocks if you can that can mimic your downstream dependencies and put latency measures into those so that you can simulate a lot of different situations and see how your endpoints work or whatever you're responsible for developing works under various situations. And find the breaking transactions per second rate. The more you break, the more you find where you can optimize. And the more you optimize, over time, the confidence builds because you know that as you're doing these discrete scale tests, you're going past the point and you're identifying on a single instance, one process, what it can handle. Then you go to the soak and you try to figure out, okay, maybe that's 80% of where I broke. Can I sustain that indefinitely? Do I have memory leaks? Does it work for a long period of time? And figure out what that percentage is. Measure response time, throughput, transactional CPU, IO heap, and then do it at scale. So now go to 2, then maybe 3, then maybe 4 containers or 4 processes, and figure out what your scaling ratio is like. And continue to break and break and break. The more you break, the more you find. You know, take from the pages of NASA. I mean, the idea here is to figure out what the conditions are like before every component fails. Then go to load testing. And within the load testing, you can, if you're dealing with really large infrastructures, you can go fractions of full scale. And then to capacity, you can really go to full scale. But you'll notice that every one of these have different goals. And because each of those have different goals, there's slightly different meanings in the metrics. And that's what really underpins and drives the value in the data. So some things that I think that you could do that would help you with containerization in Kubernetes is leverage namespaces for each of these goals and run them concurrently. Widen the pipeline. Do more in the same amount of time. And in doing that and collecting that information, you can do some probably pretty cool things with etcd. For example, keep a 2-hour exponentially weighted moving average of your response times and throughput, track your consumers, and consider using the data that you collect out of breaking your application repeatedly to tune your stacks, to govern the instance and pods, and do dynamic stack tuning within threads, pools, workers, et cetera, instead of having front ends that have a whole lot of workers. Tune those down and adjust them accordingly. It's going to maximize the efficiency of the resources that you have to work with. And then establish resource limits within your containers and pods, obviously based on this empirical data that you've collected over time. The idea here is to do continuous testing, just like you're doing continuous integration. Always be testing, always be collecting these metrics, and make them consistent. Just some final thoughts. The more hypotheses that you can test simultaneously, the more lean and more efficient your pipeline is going to become. Strive for that continuousness, establish Sigma, and track trends and adjust when necessary.
What's the Sigma?
Sigma is a statistical term. Standard deviation, that's right. It's often used in particle physics and everything else. It's the idea is you get a lot of data points, you're going to find the pattern, right? All right. Any questions? No. All right. Well, thanks everybody for being here. I appreciate it.